And now we're moving to what we call coherence, which is a concept very similar to intertrial coherence. So coherence is between two channels or two brain sources isolated by ICA, for instance. And I have the first trial, I have a second trial, and I have third trials. And here is my first process, and here my second process. I do a time frequency decomposition on each of them, and I obtain my vector. I already normalized the vector because the standard, what we call phase coherence, doesn't depend on the amplitude of the signal. So here, all the vectors have length 1. And then I'm going to compute the difference in phase between the two vectors. So this is what's represented here for this specific trial. For this specific trials, the phase difference is 90 degrees. And for phase specific trials, the phase difference between the two processes is 180 degrees. And I'm going basically to do same thing as before. I'm going to average these three vectors to obtain my coherence value. So I do this vector plus this third vector, and I'm going to obtain a vector of length about 1/3. If all my trials were having the same phase difference, like let's say all my trials they have this 90 degrees phase difference, I'm going to average all this vector, and I'm going to get a length of about 1. So the coherence tells me if the phase difference in the different trials is consistent. Like I present the stimulus, and systematically I'm going to have two processes, and they're going to have this specific relationship. Then I have a coherence of 1. If I present my stimulus and these two processes, they behave randomly with respect to each other, I'm going to have a coherence close to 0. And for those who are here in the second part of the workshop, team is going to go much deeper into coherence, partial directed coherence in multivariate data, transfer, entropy, and etc., and how all these measures are related. This is how you compute the coherence. So here I normalize my first vector. So this is for process A, this is for process B. So I normalize, I divide by the length. For the B, I do the same thing right here. And I'm going to multiply these two numbers. So I multiply the first complex number here, unitary, with the second one conjugate. And this basically computes the phase difference between the two. This computes the angular difference. And then I just do an average. So that's exactly the formula that's implemented in EEGLAB. And that's an example of the phase difference. And I'm going to, here is the amplitude on top, and here's the phase, the orientation of the final vector at the end. And here the thing we can see is that the amplitude of coupling between these two processes is larger after pictures of animals compared to pictures of distractor. And the phase relationship, so how they oscillate together, is also different. I'm going to skip this so we have a bit of time for the exercise. And this is also the reason why we don't do coherence of two channels, because if you do coherence of two channels, you don't really know what's happening inside the brain. It could be that one source is contributing to the two channels, so you really have to do very careful tests to know what you're looking at when you look at two channels EEG. So that's why we're doing ICA, and then you were looking at the coupling of all these sources. And there is problems with doing that because we're using independent component analysis, and these sources are supposed to be independent, so how can we be coupled? But we'll come back to that later. Julie's going to spend some time on this.